So we've moved on to part B of our rotational kinetic energy problem. And part B says that we have a 3 kilogram mass that is now attached to the end of our rod. And we want to know what is the rotational kinetic energy of this system. So whereas we just had the rod before spinning on its axis in the middle, we now have some sort of mass attached to the end of this rod that we want to add into our system from before. And once again, we are looking for the rotational kinetic energy, so we can just write out our rotational kinetic energy equation once again, being 1/2 times our moment of inertia, but now our moment of inertia is of our rod plus the mass on the end, and we'll get to that in a second. But to finish our rotational kinetic energy equation, this will be multiplied by our angular velocity squared, which is still the same as before we've been given, still rotating at 20 radians per second. So now we're looking at a different moment of inertia than we had in part A, because we have this mass attached at the end of our rod, this undescriptive mass, so we have to see how that changes our moment of inertia. So the moment of inertia of our rod plus our mass will be, we had the moment of inertia of our rod from before being 1/2 times the mass of our rod times the length of our rod squared, but when we add an object to our system that we're spinning about, then when we add the moment of inertias, we literally add all of the moment of inertias together. So the moment of inertia of our rod will be added to the moment of inertia of our mass, and that is going to be equal to the mass of our, mass times the distance from the mass to the center, our axis where we're spinning. So this distance right here, the distance between our mass and our axis, will be what we multiply this by, but this is squared. So our length of our rod was 2 meters, and our axis splits this rod in half, so this distance here is going to be 1 meter. And that 1 meter is going to be equal to the r that we're multiplying inside of our moment of inertia of our mass. So this entire thing, this entire equation, is what is going to be put into this one I for our kinetic rotational energy. So we can just put that down here so that it's all one big equation all together. So we have 1/2 times our I, which is altogether 1/12 times the mass of our rod, which is 10 kilograms, times the length of our rod squared, which is just 4. 2 squared is 4. And then we add that to the mass of our mass times the distance from our mass to the axis where we're spinning, and that would be 3 kilograms, a 3 kilogram mass. And then this is just 1 meter for our distance, so 3 times 1 is 1. And then all of this is going to be multiplied by our angular velocity squared, so 20 squared. And once again, all we have to do is plug this entire thing into our calculator, so we can do that real quick. And what we end up with should be a bigger number than what we got last time, because our moment of inertia ended up getting added onto. So what we actually end up with is 1,266.6 joules. And of course that ended up bigger, like we said, but what we really wanted to see was adding an object to our system, making this moment of inertia bigger, and it made our moment of inertia's equation itself much longer, and so things can get jumbled up. Just make sure that you write it out separately so that you make sure you don't forget anything. So if this number hadn't ended up 1, it would have had to have been squared, but 1 squared is just 1, so we didn't have to worry about that. But we would have in any other case. But regardless, we have finished part B, and we can move on to part C of our problem.